If you can't see it, let me know. So we covered some of this in the panel discussion, but I'm going to go into a little bit more depth about what is the Kubernetes resource model and how it enables what I call configuration as data. So we talked a bit about infrastructure configuration. Anybody who's done it or even seen it knows that infrastructure configuration is hard for a number of reasons. Infrastructure APIs are verbose, as Joe mentioned, but they're also inconsistent and not necessarily designed to be declarative. That really shouldn't be surprising because they were designed to be programming interfaces. Infrastructure as code is a fairly common way to manage configuration. It's considered by many to be a best practice in the industry. It refers to two ideas that kind of get mixed together. First, managing infrastructure configuration using the same tools as code. That has the benefit of leveraging tools that many developers are familiar with. Second, representing infrastructure configuration as code that needs to be evaluated in order to generate the configuration. Infrastructure as code tools aim to simplify the programming of infrastructure APIs. However, I've seen thousands of configuration files for hundreds of different tools using dozens of different configuration formats, and virtually none are as simple as users would like. So I'm going to talk about an alternative to representing configuration as code, which I call configuration as data. These are examples of Ansible and Terraform templates. Because infrastructure as code tools generally assume they solely control the desired state of resources under management, and you could get some of that by, from what Joe mentioned about controlling the replicas field in autoscaling, for example, which is an example that comes up a lot. All configuration changes generally need to be made using the templates of these tools. This tends to drive templates towards maximum flexibility until they become essentially struct constructors, where the structs are declarative representations of all the resources provisioned by the templates. Templates like these are effectively opaque to other tools. The only way to modify them is for a human to edit them, right? So these tools do have plugins with interfaces, but they're designed to be invoked only through the tools. Reusing them without the tools can be done, but it's a pretty heavy lift. So input variables, template input variables become the de facto APIs to the managed resources. The templates exposed, the attributes exposed as variables are often quite similar to the original APIs, but they aren't formal APIs. So consequently, it's harder to build on top of input variables. How can tools find the variable values or variable schemas? What are their semantics and their compatibility guarantees? There's no standard approach to these issues. That's because templates are designed to be an interface for humans, not for automation. It's possible to generate forms to enter the values, and sometimes users template files of input values and attempts to whittle down the complexity. But I haven't seen a lot of examples of automation built to target template input variables. They're almost exclusively generated and consumed by the templating tools themselves. This has resulted in relatively limited automation, such as invocation in CI/CD pipelines for continuous delivery of self-managed configuration, and template catalogs for automated provisioning using off-the-shelf configuration. Kubernetes has taken a different approach centered around its declarative APIs and control plane. At a high level, the Kubernetes control plane can be thought of as a document store and asynchronous controllers that operate on it. Its API server provides REST-like APIs that support primarily CRUD operations, create, read, update, delete on resources. All the persistent resources are stored in the etcd key value store. All other system components, including the scheduler and kubelet, are controllers. Both the end user clients and controllers implementing the Kubernetes business logic interact with the same APIs. Just a second. I coined the term Kubernetes resource model, or KRM, because I thought the term API overemphasized operations. In the declarative model, the resource content is primary rather than the operations, which should be the same across all resource types. That's especially true for custom resource definitions known as CRDs, which share a common implementation in the Kubernetes API server. While config maps provides storage for application configuration with controller-friendly API features, such as patch, optimistic concurrency, and watch. API extensions such as CRDs enable a number of type-specific control plane behaviors, including authorization policy and schema discovery. It's these API extension mechanisms that make the Kubernetes control plane general purpose. It can be used to control pretty much anything. And we can see from the public clouds that there's no bound to the number and variety of possible services. As you probably know, this is what a Kubernetes resource looks like. A key aspect of the Kubernetes resource model is its uniform declarative metadata, such as names and labels. Yeah, as you probably all know, this is what a Kubernetes resource looks like. A key aspect of the Kubernetes resource model is its uniform declarative metadata, such as names and labels, along with consistent operations. Consistent metadata enable bulk operations in clients like kubectl. KRM also encourages declarative references and sets, so no aliases, dynamic substitutions, or imperative group addition removal operations are necessary. However, one thing that's currently missing from the model is the ability to automatically find cross-references. Object references and label selectors can appear in a variety of fields, in different forms, and a variety of resource types. A few projects have built their own reference models. This one is from Customized. Crossplane has its own solution, at least for its built-in types. But the information really should be encoded in open API schemas. So that's one opportunity for improvement in the Kubernetes resource model. And of course, references also contain the desired state itself. There's no hard line between human specified intent and automatically set attributes. So both are included in the desired state. That does create this issue that Joe mentioned, where autoscalers can, for example, modify a replicas field. That's actually by design. But the observed state, as we discussed, is clearly distinguished from the desired state in the status block. So it's possible for clients to write the arbitrary resource types, but they have difficulty, as I mentioned, determining whether those changes worked or not. Because something that's currently missing from KRM is consistent status conditions. Crossplane has developed its own convention for that as well. And Kubernetes 6 CLI has also developed a spec that's consistent with the core API conventions. They're pretty similar, so perhaps they could be converged. This slide is almost identical to one I presented to Kubernetes SIG apps in early 2017. Because the API resource types are natively declarative, no additional layer is needed to interface with declarative tools. This enables serialized configuration to use the exact same resource type schemas as the API. So both tools and controllers can manipulate configuration data. Unlike most configuration tools, the approach established by kubectl apply doesn't assume exclusive control. Non-conflicting changes to the desired state can be merged so that human-driven changes and automation can interoperate. And it's come up several times already. Autoscaling is a canonical example. Horizontal pod autoscaler can modify the replicas field of deployments or replica sets through the API server rather than through configuration templates. Finally, the declarative eventually consistent model enables configuration transformations to be decoupled from the realization of a desired state. The decoupling of the tooling and provider layers in Kubernetes has really enabled both to flourish. Instead of implementing support for every individual resource type or API in every tool, support for KRM can be added to tools generically. This drastically reduces the integration effort. This is how there can be more than 100 configuration tools in the Kubernetes ecosystem using every imaginable syntax: Go templates, Jinja, HCL, JSON, Q, Starlark, Python, TypeScript, Ruby, etc. It's also how there can be literally thousands of unique CRDs controllers also written in a number of languages. They're not all just written in Go. Crossplane leverages the Kubernetes control plane as its own using these API extensions. And much as Crossplane has, Google Cloud has taken advantage of the API extensions with its config connector, which represents Google Cloud resource types using the Kubernetes resource model. The Kubernetes control plane is increasingly being used as a declarative platform to manage arbitrary infrastructure resources and services, not just Kubernetes workloads. The systems it manages don't have to run on Kubernetes at all. Kubernetes provides an open, consistent, declarative, universal control plane that can drive heterogeneous systems. As a demonstration of the data-centric model in action, this example shows Terraform targeting the config connector using the new provider that leverages server-side apply. Similarly, Ansible has been using the Kubernetes dynamic client. Clients like these can operate on arbitrary resource types without code generation. Another benefit of the uniform data model is that it becomes straightforward to apply policy constraints to arbitrary types that use the model, as in this Istio constraint, because Istio uses the Kubernetes resource model to configure it. Kubernetes supports enforcing such constraints synchronously and validating emission control, providing those guardrails that Bassam mentioned. And because configuration is expressed using the same representation as the API, policy constraints can also be validated prior to deployment. Additionally, Gatekeeper expresses constraints using the Kubernetes resource model, so infrastructure applications and policies can all be managed identically. And it's not just validation that can be performed prior to deployment, mutation can also. With configuration in a simple, consistent data format, that YAML that everyone talks about, we can actually extend our ability to transform configuration into configuration, authoring, change control, and deployment processes, which provides the opportunity for human review and revision if desired, but without compromising the ability to merge human intent and automated changes, as in the auto-scaling example. Now, auto-scaling benefits from a tight control loop, so I wouldn't normally want a human in the loop, but there are other types of common changes that would be useful to automate, such as security settings, which otherwise permeate and complicate templates and cause abstractions to leak. So here's an example using what we call KRM functions in kept that matches the pipeline diagram, generating, transforming, then validating configuration. I'm not showing the function code or the YAML because it's not necessary to look at either in order to do this. Unlike with infrastructure as code templates, one doesn't need to manually modify a configuration generator program or even its input parameters. Instead, one can just add a transformation that makes the desired changes or run the transformation in place. This is possible because the transformations operate on well-defined data, the API schemas, right? There is still configuration code, but it's separate from the configuration data and therefore can be reused through composition. That's really how we can take these smaller pieces and build up to more complex scenarios. So configuration transformation functions and asynchronous controllers like autoscalers enable configuration to be automated without the conceptual overhead of another layer of abstraction, because every additional type does add some amount of overhead for users. That approach is good for surgical horizontal changes like security settings, but abstractions can help to reduce the configuration surface area more significantly. And we tried several approaches to abstraction in Kubernetes. One approach we applied was multiple specialized abstractions, such as with the workload controllers, deployment, replica set, daemon set, stateful set, and job. Each provides behavior targeting a specific type of workload, but they all use the same pod template spec. They don't abstract pods at all because pretty much all pod features are needed for all workload types. We also created extensible abstractions with multiple implementations, most notably Ingress, but also network policy and custom schedulers use this approach. The main disadvantage is that we don't have a great way to express and discover the extensions. Extended attributes are specified using annotations. Finally, we partitioned abstractions to separate consumer and provider concerns, such as with persistent volume claim storage class and persistent volume. That pattern enables consumers to specify a minimal number of attributes, such as the amount of storage capacity needed, and more complex configuration to be factored out and amortized across multiple uses. That last approach is, I think, the most effective pattern for reducing configuration complexity. We applied it to workload controllers and pods using mutating image control, such as with pod security policy. And the new gateway API that succeeds Ingress also uses the pattern. Crossplane uses the claim model for infrastructure requests as well. And while the pattern is more complex end to end, it shifts the burden from the consumer to the provider. Regardless of what type of management abstraction it is, frameworks like KubeBuilder are making it easier and easier to build new abstractions on the Kubernetes control plane. And the APIs for the abstractions can be targeted by arbitrary tools and other controllers like any other resource types. There aren't abstractions that exist only in code written in a particular language or in templates for a particular tool. So In short, I just have two main takeaways. First, whether you want to build a new system or just automating an existing one, whether it has anything to do with containers or not, consider using the Kubernetes control plane and resource model. They aren't perfect, but they do continue to improve, and you'll be able to take advantage of a large and growing ecosystem. And we may eventually, decouple the control plane from the rest of Kubernetes entirely, although it's actually possible to do it to some degree today. And second, try to manage configuration as data rather than as code. And I believe it will result in more maintainable, reusable, automatable configuration. So instead of templating YAML, generate and manipulate it. We've really just scratched the surface of what's possible using that approach. And I'll share the slides on Twitter. So in the speaker notes and at the end, I put a number of links to some of the historical PRs and issues and other documents and references for almost all the examples. For example, the initial write-up on the approach for configuration in Kubernetes, PR 1007, is that first link here. So anyway, thank you.